And that's it, I think. Okay, so welcome everybody to second lecture of Science of Storms. And today we are going to talk about actually some storms. The largest scale storms on this planet, mid-latitude cyclones, also known as extratropical cyclones. I will start this lecture just with a few slides and then I will transition to the blackboard. So these are examples of mid-latitude cyclones or extratropical cyclones. Really, there is no difference between mid-latitude cyclones and extratropical cyclones. Quite often, when people say extratropical, for some reason they think it has to be very strong cyclone, but it's not really. There is no some quantitative measure to distinguish any mid-latitude cyclone from extratropical cyclone. As the name suggests, they form in mid-latitudes, where we actually are now. And then in the next lecture, we are going to talk about hurricanes, which are also cyclones, but profoundly different in structure compared to these. And here you have two examples, and you can see how they look like a comma. They are curving in. And you can clearly see, I mean, you cannot clearly see, but you can probably infer that the circulation is counterclockwise. And there are these bands of clouds that you will also, after today's lecture, hopefully understand how clouds form in something called cold front, warm front, and so on. So the size of these systems is thousands of kilometers, and they occupy entire depth of the troposphere, which you should know now in mid-latitude is about 10-11 kilometers. And they can produce all kinds of storms. Now the question is, you see, these were rotating in counterclockwise direction, but this one seems to be opposite. So why is that the case? How can cyclone rotate in the clockwise direction? This is about Australia. Everything is upside down in the southern hemisphere. That's because the Coriolis force in the southern hemisphere deviates everything to the left. But we'll examine that. You will understand soon why cyclones in northern hemisphere rotate counterclockwise in the southern hemisphere clockwise. Here's another, just to show you a scale, another mid-latitude cyclone over the United States of America. It's huge. It's the entire continent, and once again, it looks like a spiral. You will notice here, for example, how you have I would say you can see thick and localized clouds, and then over here, you can see the clouds are much wider, spreading far away, far ahead of this zone. And you will see that that zone is warm front, and there is also something called a occluded front. And just as a picture, there is a difference between mid-latitude cyclones on the left and hurricanes or tropical cyclones on the right. You can even see it with your own eyes. And the biggest difference is that visually the biggest difference is that the tropical cyclone has the eye, very cloud-free region in the center of the cyclone. But as you will see from today's lecture and then next lecture, there is also dynamically profound difference between these two weather systems. Now, here are isobars. Isobars are these lines, thick lines. These are lines of constant pressure, as we talked about in the last lecture. And you can see how these isobars are closed. And you can see how they're packed together very closely. And you saw in the previous lecture that the pressure gradient force is proportional to pressure gradients. So pressure gradient is change of pressure over distance. So very packed isobars indicate that you have very large changes of pressure over very small distance. And you saw that winds are driven by pressure gradients. So consequently, you get very, very high wind speeds in and around the center of these extratropical cyclones. One more time, you can see it because pressure lines are so close together, which means pressure gradients are high, which means pressure gradient force is high, and that is what drives winds, okay? Now, these thick black lines with triangles and half of a circle are cold fronts and warm fronts, which we will discuss soon. And then we also have these line, the triangle and half a circle together next to each other. These are so-called occluded fronts. So this is a extratropical cyclone that impacted Great Britain and Scotland. So you can see the map. So here is Italy, here is Spain, Central Europe, Great Britain. And wind speeds in this particular wind gusts exceeded 140 kilometers per hour, very high, and a lot of damage was caused in Great Britain. Okay. So the last slide is what type of severe weather can we expect from extratropical cyclones: heavy precipitation, lightning, hail, freezing rain. By heavy precipitation, I also mean heavy rain or heavy snow, and also severe winds. Okay. So so that was that was introduction to stop sharing. That was introduction to tropical, extratropical cyclones. And now the question is, how do they form? How do we get these weather patterns in our atmosphere? It's probably, to explain that properly, just like anything in this course, you need 3-4 lectures to explain extratropical cyclones. There are many mechanisms that form them. In this first hour, I'm not going to talk about any mechanism that forms them. And then in the second hour, I will talk about 1 or 2 mechanisms. But in the first hour, we will set up the field to understand how they form. And the first thing that we need to understand is something that we kind of defined in the last lecture, and that's the concept of air mass. Now, we never mentioned air mass in the previous lecture, but we mentioned something called air parcel. Air parcel is usually something small, like this room, some imaginary volume of air. Well, air mass is a huge volume of air. Okay? Air mass is an air parcel that has horizontal dimensions of thousands of kilometers, and usually depth of either entire troposphere or maybe 2/3 of the troposphere and so on. And air mass is, so let's say you have 2 adjacent surfaces, okay? So here is sea, or even better, probably say ocean, and here is land. Okay? And now you have, as we said, atmosphere, that namely troposphere, that is about 10 kilometers deep in mid-latitudes. Imagine that air over sea stays over there for several days, and the air over land stays for several days. As we saw in the previous lecture, atmosphere is modified by the land. So the air over here will acquire properties of the sea, and that is temperature and typically relative humidity. That's what matters in our case. So let's say, well, yeah, temperature 1, relative humidity 1 associated with the sea, and here you have temperature 2, relative humidity 2, okay? Now, relative humidity, I'm not going to actually define relative humidity in terms of equations now, there is no need, but it's moisture content in the air. Of course, air over sea is moister than the air over land. Now, temperatures that can differ, okay? In the summer, temperature over land is higher than temperature over sea, and it's vice versa in the winter. Because water has very high heat capacity. It takes a lot of time to heat up and cool down, okay? Whereas land quickly heats up and cools down. Now, if you imagine that there is no motion, nothing is happening, then there wouldn't be very much weather. But eventually, those air masses start moving around. And when they move around, basically that's when weather happens. When they move, they collide, they interact, they modify their properties. So the sea mass goes over land. If it was cold, starts warming up, loses moisture and so on. So there are some principal air masses on our planet, and you can see in the chapter that I assign after this lecture their exact names. But in principle, from this what we said, one fundamental type of air masses are land, and we call those continental. It's just fancy. I mean, it's not fancy, but we don't call it land mass, we say continental air mass. And the sea or ocean one, we call maritime. Okay? It's just labeling. And now you could, of course, conclude there are maritime air masses from mid-latitudes, from Pacific and Atlantic Oceans in mid-latitudes. There are maritime air masses in tropical regions. There are continental air masses in the mid-latitude regions of continents, particularly Canada and Russia. There are continental air masses in the tropical regions and so on, okay? Any questions about this? Okay, so the next thing is, imagine you have two air masses. Now, if this is north and this is south, okay, then generally we know the temperature decreases with latitude. North pole is colder than tropical regions. So let's say here you have cold air, and here you have relatively warm air. And just like what I described here, and these cold and warm air masses are separated by a zone, but we represent that zone as a line. Okay? And this line is called atmospheric front. Now, there are several types of atmospheric fronts. Type number one is the front is not moving. That means cold air is not moving south, warm air is not moving north. And we represent, these are called stationary fronts. So cold front is represented with triangles pointing away from cold air, like so. And these should be blue triangles, but I don't have blue chalk here, so this would be cold front. Warm front would be hemispheres, half of a circle, painted in red, and these half circles are pointing away from the warm air. Now, this is a nomenclature for stationary front, and this indicates that neither of these air masses are moving, okay? Now, it's never, of course, they are not moving. Maybe they're oscillating a little. There is no pronounced movement, okay? So stationary front. Now, of course, we could also have cold, warm air. Of course, this is in the horizontal plane, X, Y. We could have cold, warm air separated, but actually cold air is advancing. Then we would just have cold front. And we indicated with this blue, with a line with blue triangles, again pointing away from the cold air. And lastly, we could have opposite, of course, cold air, warm air, but the warm air is advancing, so that would be warm front. So now the word front, because this theory that I'm talking about was developed in 1919 by Jakob Bjerknes. And 1919 is a time of World War I, and this fighting between two air masses resembled fighting in World War I. So people, Norwegians, called it front. Okay. Any questions? Okay. Now the next question is, how would these fronts look like in the vertical direction? So that was XY, horizontal direction. But how about, let's say, XZ in the vertical cross section? So if here is Earth surface, this is the frontal line, okay? Frontal line has a slope. It's not vertical like that. So this would be front. And when you have that horizontal line on the surface map, you plot it where the front is touching the surface. You don't plot this point or some other point, okay? So when you see front on a surface map, on an XY plane, you have to imagine that if you would go up, you're not going along the frontal line, because frontal line is inclined. So in the case of cold front, this would be cold air mass, and this would be warm air mass. And the whole front is moving in this direction. Namely, cold air is displacing warm air. And as you can see, as this is happening, there will be relative motion. Namely, warm air will start going up and above this cold air mass. And from previous lecture, first of all, we said, what is this? This is forced convection. Maybe this air didn't want to go up. It has no other option. And when this is happening, you can have clouds and usually thunderstorms, okay? So cold fronts are quite often associated with deep clouds, namely cumulonimbus clouds, as we will study later. And these clouds can create strong heavy precipitation and everything that I listed in that slide. Quite often, though, we also have a line of clouds ahead of the front, like here. So deep thunderstorms can also form dozens to hundreds of meters ahead of the front. And this has to do a little bit with the circulation in cyclones that I will discuss in the second part of the lecture. So I cannot explain that using this figure. It will be clearer later. Another reason why clouds sometimes form ahead of the front is because you see when this air is going up, it's a disturbance. And disturbance creates waves. So in the atmosphere, you get waves, like so. And now on the crest of these waves, you can form clouds. So you can imagine a wave, and on the crest of that wave, you form clouds. And the third reason why clouds can form 100 kilometers ahead is that sometimes they form over here, but they advance faster than the front itself. And we will see how clouds, when we talk about clouds, how clouds can advance faster than the front, because they move and they also propagate. And you will see what is propagation, okay? Is this clear? And then we have, of course, warm fronts. Warm fronts, again, there is a frontal line that is slope, and the slope of this line can be calculated, but of course I'm not going to do it here. That requires some derivations. So here is cold air, here is warm air, but of course in the case of warm front, the whole system is moving like so. Now, what we usually say here, because warm air is lighter than cold air, we cannot say warm air is pushing cold air. I mean, you could, but it's more accurate to say that cold air is retreating and the warm air is consequently advancing, okay? Now, as this whole system is in this case moving from right to left, the warm air is once again riding along the cold air and everything is moving. But you can now imagine that this updraft here is much weaker than in the case of cold front. So in the case of warm front, we first get some weak clouds that are very high in the sky called cirrus clouds. And then we get clouds at mid levels known as altostratus clouds. And then we have deeper clouds somewhere here known as nimbostratus. And nimbostratus are these clouds that I just mentioned during our informal discussion before lecture. Nimbostratus are clouds that last for quite a long time, sometimes days, and can produce long-lasting precipitation and snow in form of snow, rain, and so on. So if I go back now to the figure in the XY plane, if this is cold front, advancing, you should immediately see it is advancing from left to right. What would be, if I would ask you, what would be weather associated with this front? You should probably answer that there might be thunderstorms right next to the frontal line. Now, they don't have to be lines, they can be isolated. And there might be thunderstorms ahead of the cold front. Okay? If I would ask you what is the weather associated with warm front, that again in this case is advancing from left to right, then you should say there is a very wide zone of clouds. Here, you don't have precipitation, you have just those small clouds, very high clouds, cirrus. Then they transition to altostratus, then maybe sometimes stratus, then nimbostratus. I don't have time, of course, now to describe altostratus, stratus. These are not thunderstorms, so I will skip them. Okay, you can read on your own and ask me later. But this is already something that you can use in your everyday life. Because if you look out and you see cirrus clouds, and then a few hours after that, you see altostratus clouds, namely the base of the clouds is lowering and the clouds are getting deeper, you might say warm front is coming. And eventually you will end up with precipitation that can be in the form of snow, rain, it can also be freezing rain, it can also be snow pellets or sleet. And then the sky will be clear and there will be a rise of temperature after the front passes. Does this make sense? Now, let's say here is the surface of the Earth, and this is the height, Z, okay? Let me think how I put this. And we have two columns of air. Here is cold air, here is warm air. If you measure pressure in this column and this column at the surface, where do you expect higher pressure? Underneath cold air or warm air? You people online can also speak. Is pressure higher in the cold air or warm air, close to the surface? In cold air. You can think about it from kinetic theory of gases. Cold air, there is very little jiggling of molecules and atoms, so they're compact. In the warm air, they're bouncing a lot, so the air is more spread. So when they are packed together, you can stack more molecules and atoms on top of each other. So this is denser than here. So you could say that pressure here is higher than pressure here. So let's say here is 1010, and here is 1005. hectopascals. Okay, that's usually unit of pressure. Or in atmospheric sciences, we also sometimes use that ugly unit of millibars. It's just historical, unfortunate. One hectopascal is 1 millibar. Okay, so if we are here, and now I ask you, how is wind going to blow? But I have to tell you, this is northern hemisphere, and this distance is, let's say, 1,000 kilometers. So this is not two adjacent air columns. They're far away from each other. How is wind going to blow in this case? Knowing what we learned in the previous lecture. You say it's going to blow from here to here, right? Anybody else thinks something else?
Far away? Is it pretty far away?
Yeah, they're very far away. So that the Coriolis force can kick in. Yeah, if there is no Coriolis force, he is right. The air tries to equalize the pressures. I mean, the pressure gradient force. But in the case of the Coriolis force, what will happen? So what will happen is what he said. The air starts moving from, this is 1010, this is 1005. The air starts moving from here to here. But this is northern hemisphere, so Coriolis force turns that air to the right. And then let's say here, you would actually end up with air coming out of the blackboard. It would be positioned in a way that to the left is low pressure, to the right is high pressure. In other words, the wind would blow into my back. Okay? Makes sense? So it starts moving like that, but it's curved to the right because this is northern hemisphere. Now, there is something that I will tell you that I didn't tell you in the previous lecture. But you could conclude from previous discussion, in cold air, pressure decreases with altitude faster than in warm air. So if you move 200 meters in altitude, pressure will drop faster in cold air than in warm air. This can, of course, mathematically be demonstrated through famous what's the name of the equation? No. Anyways, this equation. So this equation is telling you how pressure decreases with height. It will cross my mind in a few minutes. So this is pressure at the surface, gravitational acceleration, Z is height. This is gas constant for dry air, 287 joules per kilogram per Kelvin. This is temperature, average temperature in this column of air. This equation can easily be derived from that law, that great law that we derived in the last lecture. From hydrostatic equation, you can derive this by substituting rho from the equation of state and then integrating. But this equation is telling you that the pressure, you can examine it later, that the pressure in cold air is dropping with altitude faster than the pressure in warm air. So that means I go to this height. Pressure here might be now 1,000 millibars. And over here, it might be, I don't know, now I'm messing this up. I should get better numbers. But, well, let's say again, here is also 1,000, okay? Because here it dropped for 10 millibars, here it dropped for 5 millibars. What will be wind? There is no wind, nothing. Now you go higher here. Now here, pressure might be 990, and here pressure is 995. Do you agree with me? Do you see how is wind going to blow? Well, now it blows from here to here. And because this is northern hemisphere, it will go into the page. Now you go here, you go here. Here is 990, but here dropped to 980. Now this wouldn't be linear because you see this is exponential function, but I'm just simplifying things. So these are larger pressure gradients, therefore you will have stronger winds. So the wind will be even stronger into the blackboard. And you can see that when you have temperature differences, I told you in the previous lecture, in wind engineering, people say, oh, geostrophic wind is constantly high. That is only case if there is no temperature differences. If you have temperature differences, you start having change of these are all geostrophic winds, but they're changing with height. And change of geostrophic wind with height is known as thermal wind. And then at the end of the troposphere, you end up with very strong wind known as jet stream. Okay, these are the strongest winds on our planet, exceeding 200 kilometers per hour. There is no stronger winds that our planet is producing. Where are the largest temperature differences? Well, across the fronts. Because what we discussed, what is front? Let's say here is north, here is south. Here is minus 10 degrees Celsius. Here is minus 5 degrees Celsius. Here is 20. Here is 10 degrees Celsius. This is air mass A, this is air mass B. Where these two air masses collide is where you have front. So you have very strong temperature differences. Namely, the frontal zone is 50 to 100 kilometers wide. Thick, I mean wide. And the temperature difference can be 10, 20 degrees Celsius. Something that you would find over 1,000 kilometers in a uniform air mass. Does this make sense? So why am I telling you about jet streams? Well, I'm telling you about jet streams, and I'm finishing with this, because they will play extremely important role in the formation of these extratropical cyclones. And fronts will also play important role. They play important role, as you can see, they are associated with jet streams, but you will see a few other ways how they are also important. Are there any questions in classroom or online? And we go for a break. No questions. Okay. I will pause recording, and you can also, people online, you can think of questions and then ask later. Now, how do I pause recording? I always here. It's okay. So recording should be back on. I'm unmuted. Everything seems to be okay. Okay. So let's talk about extratropical cyclones. Before formation, I will first just describe how they look like. So a cyclone has to have closed isobars. So lines of constant pressure needs to be closed. Now, this means closed, of course, isobar, but when we plot them on a map, we don't close them because you have to put value of the pressure. So we leave here a little bit and you say, for example, 1,000. That means 1,000 hectopascals or 1,000 millibars. And then as you move in, there is yet another closed isobar, namely line with constant pressure, perhaps 990. And over here was perhaps 1,010. And then maybe there is last one that is not closed, okay, like so. Because in principle, if there is no disturbances in weather, isobars tend to be parallel to the latitude lines, okay? So this might go, I mean, it's never valuable like this. So we denote cyclones with L. L means low pressure in the middle, okay? So if you could visualize this in 3D, it's like a sink, okay? Low pressure in the middle, and then as you are moving away, there is high pressure. If I pick a air parcel over here, let's now discuss what is the composition of forces that we studied in the last lecture, with addition with one more force. What would be direction of the pressure gradient force of this parcel? Towards the center, away from the center, or in some other direction? pressure gradient force. What's that? From high to low. Pressure gradient force is always from high pressure to low pressure. So the pressure gradient force would be like so, right? Pressure gradient force. So the air will start moving towards the center of the cycle. But there is another force clearly that will act, and that's the Coriolis force. And Coriolis force will turn this to the right. So eventually you will have wind that is circling around in counterclockwise direction. So to the right, we have Coriolis force, but is there another force that is helping Coriolis force to balance the pressure gradient force? There is centrifugal force, because now you have a circle. Look, this air parcel is going in circle. So there is centrifugal force, CFF. Okay? Pressure gradient force, so somewhere here is high pressure, here is low pressure. Pressure gradient force always exclusively acts from high to low pressure. Coriolis force acts to the right of motion, and centrifugal force as well. Now, I know that this can be confusing, because you might say, well, how did it get here? Okay. Typically, let's just plot two isobars. Okay, here is P, here is P plus delta P. What will happen? This parcel of air will start moving towards low pressure. And then Coriolis force acts, and you get something like this. Does this make more sense? This part over here is called geostrophic adjustment. So it takes, but we don't usually, we just, what I plotted here is the final state, as you can see. But to get to final state, you oscillate. Just like when you drive a car and you're not a good driver and you overturn and you compensate and eventually you find your way. Does this make sense? So you see, we now have, what's the name? Equilibrium of three forces. Centrifugal force, Coriolis force, and pressure gradient force. Equilibrium of these three forces is known as gradient field. You remember from last lecture, pressure gradient force plus Coriolis force equals 0. That was geostrophic wind. Pressure gradient force plus Coriolis force plus centrifugal force equals 0. That's gradient field. So geostrophic wind is the special case of gradient wind when the isobars are straight, when there is no centrifugal force. In terms of equations, it's not that simple, complicated to just immediately figure out equation for gradient wind. Because now, because in the case of cyclones, they are circular. So we usually use polar coordinate system. You put some axis R, whatever, that is radially out of the center. It's much more easier than using X and Y coordinate system. So here, the pressure gradient force is negative 1 over rho, delta P, delta R, right? Pressure gradient across that plus Coriolis force is Coriolis parameter times some velocity V, and plus centrifugal force, which I forgot. I think it's V squared over R, where R is radius of curvature at the distance of this air parcel. And that needs to be equal 0. When this is satisfied, this wind V is known as VGR, gradient wind. But you see, this equation is more complicated. This is quadratic equation, so you can get many solutions, in fact 4. But I don't have time now to go, because this equation also describes what happens when you have high pressure in the center, and so on. But you can watch my YouTube channel to figure that out, or even better, you can find some good book to study that. Okay, I don't have time in this lecture. But solution of this equation is not just cyclones, it's also anticyclones and so on, and some other anomalous cases. Is this clear? So you know the difference between gradient and geostrophic gradient. Okay, so that was generally how cyclones look like in terms of the pressure field, how wind circulates in counterclockwise direction. And also now you see in the southern hemisphere, Coriolis force act to the left, so they will rotate in clockwise direction. Now the question is, how do they form? And that's what we are going to talk about for the rest of this lecture. How do we get from nothing to that? And I'm exhausting all charts. So first, we can look into the formation of cyclones from the point of view of surface variables, namely what frontal properties are at the surface. So we start at this stationary front that we defined. So here is north, here is south. So here is cold air, here is warm air. And you remember this was symbol for stationary front. This should be red, this should be blue, but okay. And this is stationary front, lines, let's say, parallel to latitudes. At the next moment in time, I don't know, maybe a few hours later, there is the so-called kink on this line, like so. Now we will discuss. Well, I can discuss now, but so this would be now cold front. This would be warm front. Okay. The cold air starts advancing like that. Warm air starts advancing like that. This cold air from here starts moving towards here, and you get something like that. Here at the apex of the two fronts, you start forming a low pressure system. You have a low pressure system in the middle because you saw that this circulation resembles cyclones that we discussed. Now, another thing, what could cause this kink in the line? The best answer is jet stream, and you will see in maybe 20 minutes how jet stream causes this. But before jet stream, as I said, this is not always completely stationary. It's maybe oscillating a little bit. And as it is oscillating, there can be difference in roughness. So this part moves more than this part, and you get some inequality, okay? And that can create kink. The moment you have this circulation, you know that in the center of circulation, you have a low pressure system. It's not very high, it's very low pressure system, but it starts forming. From here, few hours later, or maybe a day later and so on, this is transforming into the case where this perturbance is growing, just like wave of the ocean. So here you have cold air advancing, and here you have warm air advancing to the north. Now, we would say that this pressure system deepened, and the pressure here is lower than it was before, because this circulation is now stronger. This is, by the way, known as the Norwegian school of cyclone development. Again, developed in 1920s by Bjerknes, Rosby, Sverdrup, that team was also Ekman, but he didn't work on this. He worked on something else. He worked on?
On his equations.
Yes, he worked. I will maybe, I don't know if I maybe I will talk more about that in some other lectures, okay? It is very important in boundary layer meteorology. Is this clear, this concept? Okay? Now, as this system is growing with time, then we end up in the next stage, maybe I put it here. We end up in the next stage of cyclone development, and that's called occluded. Occluded cyclone, which I will explain soon. You see, cold front is generally moving faster than the warm front. Cold air is advancing faster than the warm air. So you see this front, as it is advancing, it is catching this front. So you end up with something like this. Where here you have cold front, very well developed. Warm front is very weak in terms of it almost doesn't exist. And you have this over here, which is called occluded front. Occluded front is indicated as triangles and half circles, like so. And now I will explain vertical structure of the occluded front. It's not all easy to visualize from here what is happening. But I would like you to understand what happened, how we get from here to there. This line, namely cold front, is moving in this direction much faster than this line is moving in that direction. So you get overtaking of cold front. Cold front is overtaking warm front. And that's this, okay? This front advanced all the way here, and then you get this, which we call the occluded front. What is occluded front from the vertical point, from the vertical cross-section point of view? Where is the lowest pressure? Here, in the apex of this occluded front. Okay. So if you would take a line like so over here, okay, and now you plot vertical cross section. Here is height. Let's say, let me think. No. Let's say this is point A, this is point B on the line. So I put here point A and somewhere here point B. You would have front that looks like this. Here is very cold air. And then somewhere here you get cool air. Not so cold compared to this air. So cool means cold, but not as cold as cold. I don't know. I'm not native English speaker. That's what they told me. Okay. You can write a little bit less cold. And the warm air is pushed up, warm. Okay. This is called occluded front. And the whole system generally moves like so, in this direction. So everything is translating like that. Okay. Is this front producing storms, huge storms, particularly here? Because look, this warm air is pushed so high, it has to slide above these two air masses, you get very strong storms. And generally, they spread pretty much everywhere. Now, of course, the strongest ones are usually here at the connection of warm and cold air masses. These are called occluded fronts. And they happen, now there is also, this is called cold front occlusion. There is also warm front occlusion. Forget about it, I cannot explain everything, okay? This is more common. Happens because cold air is advancing faster than warm air, overtakes it, and you get this. So you can see if we go back to these figures that I showed you, I don't want to now connect PowerPoint and lose time. But you will, I hope, remember that we had, I said there is extratropical cyclone from satellite images. There was usually a band of clouds like so. And then sometimes, sorry, in this region, you get wider area of clouds. This is because warm front is somewhere here, cold front is here. And then in the center, you get a lot of clouds. Because in the center, you are in occluded front. In occluded front, you have clouds everywhere. So you get clouds everywhere. Here is a head of warm front. Here is a head of cold front organized storm. And you get this kind of coma shape. Does this make sense? So there are 3 stages in this Norwegian school. This is called cyclogenesis, genesis of cyclones. First is pink or perturbation on a stationary front. And then, I don't know our official names, but then the second stage is mature stage or growth. And then the third stage is this occluded stage. And this is where the front starts dying. Because you eventually, this cold and cool air start having similar properties. And then the temperature differences between these are small. And then the whole system is weakening. Because we said when you are in the same air mass, nothing is particularly happening. Okay? Now, quite often, so this front can die off. This small patch of warm front can then, now sometimes it extends like this, where it is again stationary front. I know people online don't see it, but that's the price you pay for not being in person. I'm kidding, I'm gonna rotate. Okay? Do you see it? No, you see it. So you see this cyclone dies, but you have new perturbation over here and maybe new cyclone develops and so on. Cyclones generally travel from southwest towards northeast, and they last 4 to 5 days, okay, from the moment of their initial formation to dissipation. So that's why, for example, the region west of, I guess, southwest of Alaska is known as graveyard of cyclones. Many cyclones form more southwest travel there. There is also many cyclones form over the east side of Rocky Mountains and then cross North America and then move towards northeast Canada and the Atlantic Ocean and so on. That's why that region of around Iceland is constantly low pressure. Many cyclones go there and die off. Okay, one of the reasons. Is that clear conceptually? Okay. Now, of course, another question that we will maybe finish this lecture with is how is, yeah, go. Another question is how is this whole thing related to jet streams? Why did I talk about that? Jet streams usually develop in entire planet. Okay, they are a few hundred kilometers wide and only a few kilometers thick. They are very thin, very long and somewhat wide. Okay, and that's one of the reasons why when you fly from Canada to Europe, it's always faster than flying from Europe to Canada, because you're flying against all these winds and all these jet streams. Jet streams blow from west to east, and airplanes can catch a little bit of that and then move faster to Europe. Now, let's say this is a jet stream, okay, in the XY direction. So this is north, this is south, this is east, this is west. And jet streams are meandering and not completely straight. They have this curvature for various reasons that I'm not going to go into. These are known as Rossby waves. You can read more if you want of Rossby waves. But look at this now. This is a gorgeous piece of atmospheric dynamics. Let's take parcel of air here. Okay. You can see that this, oh, by the way, these are isobars. Okay, so pressure PP minus delta V. Look at this parcel there. It will move like so, right? Low pressure on the left, Coriolis force is acting to the right. These two forces are in balance. You can see that this part of the jet stream is straight, so there is no centrifugal force. We can assume this is geostrophic wave. Now, how about here? It's very important to know that I am assuming that the thickness of these lines is constant. I don't know if I properly got, but they are not. This should be all same thickness. How about here? What is the composition of forces over here? I don't want to finish this arrow because this arrow might be longer or shorter than this one. So that's what we want to discuss. Pressure gradient force is acting in this direction. This should be clear to everybody. From high pressure to low pressure. Coriolis force is acting in this direction. Am I right? Coriolis force is acting to the right. But now there is centrifugal force. This is the curvature. So there is centrifugal force acting like so. Make sense? So consequently, wind speed here will be weaker than here. But why would wind speed be weaker? I mean, why the fact that you have two forces here results in wind speed being weaker than in this case? That's the reason is Coriolis force only depends on wind speed. So here Coriolis force is a low balancing pressure gradient force. And because it only depends on wind speed, you have to have high wind speed for Coriolis force to be high. But here Coriolis force has help of centrifugal force, so the wind speed doesn't have to be as strong as here. Because you have second force adding to the balance of forces. In all these cases, pressure gradient force is always the simplest, it's constant, it doesn't change. And we talked in previous lecture that all other forces are reacting to pressure gradient force. As you can see, Coriolis force is adjusting here. And yeah. So how about here? What is the composition of forces over here? So again, you have pressure gradient force in this direction. Is wind going to be stronger or weaker than here? It's going to be much stronger. Because you also have now centrifugal force acting in this direction. And the Coriolis force is alone, has to balance these two. Coriolis force has to balance these two, means wind speed has to be strong because it only depends on wind speed. Of course, it depends on the rotation of the Earth. That's constant, we assume, okay? Now, the question is, how is this related to cyclones? It's very much related because you have fast winds over here and somewhat slower winds over here, and then very slow winds over here. Okay? So what you have here, if we look in vertical direction, let's say this is height. I am examining this part over here. I have high speed winds, okay, becoming low speed winds. Does it make sense? What is this known as? Convergence. Where is the air going to go? It's going to go down. And when it goes down, it is spread. These are high pressure systems. This is opposite to what we analyzed. These are called anticyclones. This is high pressure system. But how about here? Here history repeats. Here wind speed picks up and then again it's very fast over here. So if I analyze this part of the figure, maybe here. Here is horizontal direction. Here is height. Let me see if online people can see. Can you see this online people? Yes. Here is height. Weak winds become strong winds. Where did the mass come from? I mean, you are removing mass. So the mass has to come from the below. But you cannot end up with vacuum over here. So you have convergence. This is called divergence at higher elevations. This is called convergence at lower elevations. This is known as convergence at high elevations, divergence at low elevations. This is the center of the cyclone, low pressure. Okay? So question, where are you going to have a low pressure system close to the surface? Here. You will have low pressure system close to the surface. Where are you going to have a high pressure system close to the surface? Here. Is that clear? Where is the low pressure system at elevation? Here. I mean, you can see this is low pressure system. But let's write this down. This is low pressure system at the level of the jet stream. As you can see, this is low pressure. This is the low pressure system at the surface. So if you would look into that cyclone, it's not a vertical line, it's inclined. Look here, one more time, very important. Center of low pressure system is here at the surface because of that divergence convergence. Center of low pressure system is to the west at elevation. So they look like drunk person. The same is with high pressure system, as you can see. So this is also what is often studied in atmospheric sciences. And again, you can calculate the slope. It's not that easy theory. It's not important. But this is very, very important. Okay. And we will see that this is not the case in hurricanes. In hurricanes, they are straight. Low pressure system at the surface propagates upwards and actually becomes high pressure system at high elevations. But this is what happens in cyclones. Now you see, imagine this guy is moving generally to the west, to the east. And then it passes over that frontal surface. Well, this creates what we said kink or perturbation on the frontal surface. And you start having convection, air is going up. At the surface, air is piling in. Coriolis force starts acting, you start having cyclones. Okay, now how is that related to fronts? Well, I told you the jet stream is related to fronts also. So everything is hooked up together. Okay, so you have all this is also explained in book. So you have to read this a little bit, of course, ask me questions if something is not clear. But you have to understand air masses. You have to understand concept of front, battle between air masses, how fronts advance. You have to understand concept of convergence and divergence, and they are dipoles. If you have divergence above, you have convergence close to the surface and vice versa. You can also see quite often at surface maps and convince yourself after this lecture, you will have high pressure system to the west of low pressure system. You see why? So another simplified schematic of this whole thing would be that if this is height Z, and you have a sinking of air somewhere, that sinking of air spreads. Now, these are not thunderstorms and downbursts and whatnot. These are thousands of kilometers. And these are very slow. These are a few meters, few centimeters per second. And then you have cyclone. This is high pressure system close to the surface. This is low pressure system close to the surface. And this diverges over here and kind of have like this. And it is very idealized, but the point is to demonstrate that you have high pressure system usually to the west of low pressure system. And then you might have another high pressure system because those rotary waves, there is not just one wave. Usually you have multiple waves enveloping entire planet. Okay? Do you expect any thunderstorms in high pressure systems? No. Very clear sky, very cold if it is winter, because this is very calm environment. In fact, you remember these air masses that I talked about? Air masses usually, air mass doesn't form in cyclone. This is too active. This is too dull. So air masses usually form underneath anticyclones. And famous anticyclones in winter are Siberian anticyclone that is situated over entire Siberia, also above North America. We often have very deep, very wide anticyclone. So you can have air masses that really acquire the properties of the underlying surface. They can stay there for weeks. Okay. Any questions about? Yes.
I didn't understand.
Maybe not. Can you go back?
What's the correlation between the jet stream and the front?
So you remember when okay, yeah, that's a good question. You remember when I said here is cold air, here is warm air. And then when you stack these two, let's say at the surface you have wind from this direction. And then because pressure, so this is warm, this is cold. Pressure is decreasing faster in cold air, than in warm air. Maybe here you don't have wind. You start having wind into the surface, and then that wind is increasing and increasing with height. Because the pressure difference between these air masses is increasing. Pressure gradient force is increasing, winds are increasing. And over here, you have jet stream. Okay? At the top of the troposphere, you have jet stream. But why is this related to fronts? Well, it's related to fronts because the largest difference between cold and warm air is across frontal zone. Okay? So fronts are very steep gradients of temperature, and very steep gradients of temperature result in very strong increase of geostrophic wind with height. And eventually, at high elevations close to the tropopause, you have jet stream. And there are two jet streams in the northern hemisphere, subtropical and polar jet stream. Anyways, now I don't need to go deeper into it.
Okay.
Okay? Any questions online? Okay, if not, oh, your battery is low. But this is not good. Let's see what is the. I didn't bring cable, being completely confident. Let me try to decrease brightness of my screen. Look, online people, if my computer shuts down, I'm sorry, but that's very realistic possibility, okay? But basically I finished the lecture. What I'm going to say now, it's a bonus either way. So, so next time, book a ticket and come to Genoa to attend the course in person. What can I say? So as I said, this is one way you get cyclones. There are other ways of getting cyclones. Actually, rather than that, let me tell you a little bit. You remember how I said associated with warm front, you have transition from these small high clouds to deeper clouds. So generally what I said, if here is warm front, because this is science of storms, so let's talk a little bit about some severe weather here. If you have this warm front advancing like so, so generally in this region, you might expect rain. Now, if it is summer, you're just going to get rain. But let's say it's winter and it's not Genoa, somewhere where you get snow and other things. Now, ahead of rain, you might expect a zone of freezing rain. And then a zone of sleet. And then a usually wider zone of snow. Okay? Now, it doesn't, you don't get often freezing rain, but you will see why soon. But in an ideal case, this is what you can expect. So if you are somewhere here, this is how the thing progresses. Now, why is that the case? What do you think? This was warm front, you remember? So here is warm air, here is cold air, and the whole thing is progressively so. And here you start having some deep clouds, nimbostratus. These are very wide big clouds. These clouds can produce snow. Okay? Now look at this. Here is cold air. You start having snow. This snow falls to cold air, and it just happily falls to the ground, this snow. Now, how snow forms, you will not learn this. It's cloud microphysics. Okay, so you can read on your own or come to my office and ask. It's the process of aggregation. Ice particles coming together. But at any rate, you get snow here. Now, over here, you start having snow. But this snow melts because this is kind of warm air. But then it goes to cold air, so it refreezes. And you get sleet. So what is sleet? Sleet is a snow that melted and then again froze. Now you don't get snow again because the formation of snow is not freezing of liquid water, as I said. It's ice crystals, this ice crystal colliding with that one, and then third, and then fourth, and of course they grow also, but that's how you get snow. Whereas sleet is from, so this melts and then freezes. But now you start having snow from here, but this is much deeper layer. So again, everything melts, but you have only small layer of cold air, perhaps below zero. So you don't get refreezing, but the surface is below zero. So when that liquid water falls on the surface, it freezes. So you get here sleet, and here, I don't know now, let's put, you get freezing rain. Does that make sense? And over here, you just get rain. Again, a little bit about storms, because freezing rain is very nasty, of course. It destroys transmission lines, traffic, all kinds of hazards are related to it. So if you would have to plot, if here is, let me think, what is what? Here is temperature, here is height, and here is
I guess that we lost him, right?
Yes, so
So, okay.
So do we wait?
No,
I'm not
because
sure that makes sense.
no, I guess that probably he will not be able to charge to plug his laptop. This is what I got. I don't know.
Mhm.
Even because probably the lecture is going to end in less than a quarter of hour. So
I'll
yeah,
I'll drop a message to my colleagues who are in the very office, the lecture
yeah,
room.
but
So
anyway, yeah, but anyway, I think that I mean it's meaningless, it's pointless for these last 10 minutes because anyway, I'll quit, guys. So we see in the next class. Bye,
yes, yeah, next time. Bye.
Bye.
bye, guys.